Okay, so now we're going to move on to another exam. We're going to take a look at the fall 2016 exam. We're going to look at different questions on there. We'll look at question numbers 10, 11, A, B, C, and D. Okay, so question number 10 says that they want us to find the sum of the following series. I've got the sum from n equals 1 to infinity minus 3 to the n over 4 to the n plus 1 over 5 to the n. Okay, so when I see these types of things, the first thing I'm going to do is I'm going to break this apart into two separate pieces so then maybe I can decompose it from there. So let's do that. So I have n equals 1 to infinity, and I've got minus 3 to the n all over 4 to the n plus sum n equals 1 to infinity, 1 over 5 to the n. So this one here jumps out at me right away as a geometric series. Okay, so geometric series, I'm going to handle that one. Sorry, I'm finding the right lighting here. This one here, right, I've got a minus 3 to the n all over 4 to the n. This actually is a geometric series too. Let's rewrite it. Equals 1 to infinity, minus 3 over 4 to the n. This is our r. This is also geometric. So I've got a sum of two different geometric series. Okay, so I have to check for convergence on each of these and then sum them up and then sum up their sums together. Okay, but I also have to keep in mind, right, this is a common trick on the final exams. My geometric series, to do the sums, the geometric series start at 0, but each of these indices start at 1. So don't forget, we have to subtract out our 0th term. Okay, so let's take a look at this one first. Over 4 to the n. So this is geometric, and our r is equal to minus 3 over 4. So let's check. Our terms for convergence are the absolute value of our r has to be between 0 and 1, which it is, so this thing converges. Okay, that's good. Before I do anything else, I'm just going to check convergence on this one too, right? Because if this one diverges, I'm not going to bother calculating the sum. Okay, so I've got n equals 1 to infinity, n to the n. Okay, so my r is equal to 1/5. So 0 is less than the absolute value of 1/5, which is less than 1. Check. This part converges also. Good. Okay, so since they both converge, then I will check their sums. So my sum here, remember it's a over 1 minus r. The way that I'm going to handle this is slightly different than what we're seeing in the solution set that got posted online. The solution set found an a value, right? So that we basically kind of reworked our series to find a different a value so that they didn't have to subtract the 0th term. I kind of like to keep it a little bit cleaner where I have an r. In this case, my a is equal to 1, and I'm just going to subtract out my 0th term that's there. This is equal to 1 over 1 minus 3/4. Okay, so this becomes 1 plus 3/4. So keep that in mind. Be very careful when you're doing this. So 1 plus 3/4. This is 4/4 plus 3/4 becomes 7/4. Okay, so this is 1 over 7/4, which is actually equal to 4/7. And I need to subtract out my 0th term. Oops, sorry. I need to subtract out my 0th term. And my 0th term is going to come back here when n equals 0. Thing is equal to 1. So I'm going to subtract out 1. So this is like subtracting out 7 over 7. So 4 over 7 minus 7 over 7 is going to equal to minus 3 over 7. So that's my sum for this portion of my geometric series. All right, let's take a look at the other one. So here we found the r from before, so let's calculate our sum. It's equal to a over 1 minus r. In this case, again, our a is equal to 1. Right, so this is slightly different than what they did in the solution set. I'm using the a equal to 1 instead of a equal to minus 3/4. And then for their solution, they didn't have to readjust and subtract out the 0th term, but I kind of like doing it. Okay, so 1 all over 1 minus 1/5. This is 5/5 minus 1/5 is 1 over 4/5, which is equal to 5 over 4. And for that, we're going to subtract out our 0th term. My 0th term is, right, when n equals 0, 1 over 5 to the 0 is equal to 1. So I'm subtracting out 1. So this is like 5 over 4 minus 4 over 4 is going to give me 1 over 4. This is my sum over here. So my big sum, I'm going to add these two together, equals minus 3/7 plus 1 over 4. Okay, so we go ahead and add these two together. Okay, when I add them together, find the common denominator, put it all together, and I'm going to get minus 5 over 28. Okay, as the total sum. Okay, that's fall 2016. Question number 10. Okay, so fall 2016, we're going to move on to question number, we'll do question number 11. I'm trying to rearrange things here. 11A, let me just read it out. So 11A says, we want to tell whether or not it's going to converge or diverge. Let me write this down. K equals 1 to infinity, 1 plus the cosine of k all over k squared. Okay, so now what I'm going to be doing is I'm going to take a look at, right, this isn't any particular type of a test as I see it, like the one that we just did was obviously a geometric series, so I could use a geometric series test. But I'm going to take a look at the cosine. So the cosine of k essentially is going to oscillate between basically minus 1 to positive 1, right? Cosine of k. So I can actually, let me write this a little bit better. Right. So if that's the case, right, then I'm looking at my total series here. It's going to look like 1 plus minus 1 over k squared is less than or equal to 1 plus cosine of k over k squared, which is less than or equal to 1 plus a positive 1 over k squared. So 1 minus this is 0, right, and this is going to be between 2 over k squared. Oops, sorry, 2 over k squared. Okay, so basically I'm bounded on one part by 0 and the other part by 2 over k squared. So I'm going to take a look at 2 over k squared. Okay, so 2 over k squared, this is a p series, right? It's just 2 times 1 over k squared, so it's 2 times a p series, but it's still a p series. And in this case, our p is equal to 2. That comes from our exponent right there. Since the p is greater than 1, this thing is going to converge. Right? So because this is going to converge, right? Sorry, it's going to converge. Then, and it's the larger of the series, right? It's larger than the one I'm talking about here because I've got this series here. The series that converges is going to push down the one that we don't know about. So we know that the larger one's going to converge. It's therefore going to make this one converge as well. So what we just did was a direct comparison . Converges by a direct comparison test. And we compared it with a convergent p series. I worked it through. Anytime you see like a sine or cosine, always be thinking about it's going to be oscillating between its amplitude. Okay, so in this case, its amplitude is 1, right? So it's going to be positive or negative 1. Okay. And then in this case, we also have a 1 plus that. So that means that this lower bound is going to be 0, and the upper bound is going to be 1 plus that. Okay. Okay, that's question 11A. Move on to 11B. Let me bring up the question. I'll take a look at it. 11B says we got sum k equals 1 to infinity, k cubed plus 2 all over 2 k cubed minus 1. Okay. This is a pretty straightforward test here. Okay, so it's not jumping out at me as any particular type of a test. Okay, like I don't recognize it as geometric. I'm not going to use root. Ratio test is going to be, more crazy than I need it to be. But it's kind of like I've got a function over a function, right? I've got the same degree terms here, okay, which means that it's going to reduce down to the ratio of their coefficients, right? So with that kind of logic, I'm going to maybe think about the nth term test. Remember, right, or divergence, hope you remember. This only tells us about divergence, okay? So that means I'm going to say the limit as k goes to infinity of k cubed plus 2 all over 2 k cubed minus 1. Okay, like I said, it reduces down to the ratio of their coefficients, which in this case is 1/2. Okay, our nth term test says if this limit doesn't equal to 0, right, which 1/2 does not equal to 0. I have to specify that I know what that is. Therefore, this thing is going to diverge. So it diverges by our nth term test. Okay, 11C, I'll get the question. So 11C says e equals 1 to infinity, 2k squared over k squared plus 2k plus 5. And that's all being raised to the kth power. Okay, now, when we raise it to the kth power, that makes me think automatically of my root test, right? So the root test is going to help me get rid of that. So let's try out our root test. Okay, so if I do the root test, remember the root test says the limit as k goes to infinity. I'm going to take the kth root of the absolute value of this whole thing, 2k squared plus 2k plus 5. This is to the kth power. Okay. When I do this, I'm going to get is the limit as k goes to infinity, 2k squared plus 2k plus 5, because the kth root, right, these things cancel each other out, and I'm left with this. Okay, so as k goes to infinity, again, right, we're left with the two highest degree terms that we're comparing it with, and that's going to equal to 2. And our root test says if what we get is greater than 1, 2 is greater than 1, right, that means that this thing is going to diverge. Okay, and it's diverging by the root test. Okay, part 11D. You write it down and then Right, so in this particular case, we're dealing with 1 over k ln of k to the cube, okay? Anytime I see like an ln of k and I've got a 1 over k in there already, 1 over k is the derivative of ln of k, which means that I've got a derivative built into the function that I'm working with. So I can start thinking about using something like the integral test. Remember, this function starts off, remember our integral test says I have to go from 1 has to be greater than 1, so I'm going to go from 2 because that's where my series starts, to infinity, right? And I'm going to take the integral as though this were a function, x ln of x cubed, and this is dx that I'm dealing with. Okay, now this has to be a decreasing function, okay, and I'm dealing with things in the first quadrant, okay? So now, when I go to integrate this, I'm going to be thinking about maybe u substitution. So if my u is equal to the natural log of x, or du is equal to 1 over x dx, which we have right here, 1 over x dx. Okay, so then basically I can substitute this in. Okay. And let's also convert this from an improper integral into our limit. So the limit as b goes to infinity from 2 to b. Right, I'm going to do this convert from u and also my improper integral at the same time. So I've got 1 over u cubed du. Okay, and I'm going from 2 to b, and the limit as b goes to infinity. Okay, so let's go ahead and integrate that. Okay, this is my power rule, which is like u to the minus 3. So when I integrate this, I'm going to increase this by 1, u to the minus 2, and I'm going to divide by minus 2. Okay, so let's substitute back in, right, what we're trying to do here. So this is going to be the limit as b goes to infinity, minus 2 times, this is 1 over, so I'm going to go 1 over natural log of x squared, and I'm evaluating that from 2 to b. And let's write this down over here. So the limit as b goes to infinity, minus 2, 1 over natural log of x squared, from 2 to b. Okay, so now let's go ahead and do our fundamental form of calculus. So this says the limit as b goes to infinity, minus 2. Minus 2 is just a multiplier. Really what I'm looking for is what's going to happen here. 1 over natural log of b squared minus 1 over natural log of 2 squared. Natural log of 2 is just a number squared, okay? Natural log of b is going to go to, as b goes to infinity, this thing is going to go to infinity, but it's 1 over that, so that goes to 0. This is just a number multiplied by a number. So this is a positive, or it's actually just a finite number. Okay, this integral itself converges. So let's write that down. The integral converges. And therefore, our series converges. Don't confuse the fact that whatever our integral converges to, right, this integral is going to have some number associated with it. Okay, that in this particular case is erroneous. We don't care about that. We just want to know, is the integral test going to converge? It's going to tell us what our series is going to converge to. If we were asked to calculate the sum of this particular series, we would have to do something slightly different, okay, but we're not being asked to calculate the sum for our integral. So we're just checking to make sure that it's going to converge, and it does.